Mohit is here with us. He's with Flowtech Industries. My name's Phil Harris. I'm with a company called Insight Analytical. We're in Canada. We're the distributor in Canada for the JP3 analyzers, and I've worked with JP3 and Flowtech now for a number of years. We put on a lot of webinars, and so Mo and I discussed doing this one. Normally, of course, since I'm in North America, I put them on around, lunchtime in North America. But, we thought we would put one on at an appropriate time for our colleagues, in Europe and in the Middle East and the Far East, all over the world to attend. So I do appreciate you all coming. It's great doing this with an international audience. JP3 is a product that I feel particularly strongly about. I think it's a great product. I started working with them early on, and while they were still kind of in the development phases as a consultant, and then got the opportunity to help promote the technology up through Canada. So what we're going to talk about today is just kind of an overview of how this technology kind of differs from some of the technologies that you are used to, and how we can use it to optimize oil and gas operations, and generally use it as a means to produce better quality products, increase production volumes, and generally maximize our revenue and get economic payback from putting an analyzer in. Please feel free to, if you have questions along the way, you can either just put on your mic and interrupt me. I'm perfectly fine with interruptions. Or if you like, you can type a question in the chat, and then I'll try to read it out to the whole group and answer it there. So let's talk a little bit about JP3 and what they bring to the table. JP3 is produces a near-infrared spectrometer. The Verax is near-infrared. So it's an optical spectrometer. Spectroscopies generally provides us a number of advantages when we're doing measurements. And one of those certainly is that it's very fast. So it provides rapid measurement speeds. This means we can get data updates often within seconds, and 15 seconds is kind of a typical number we bandy about. And getting fast response can oftentimes help us to be able to tighten up control loops. It's capable of doing multi-parameter analysis, and so this is especially important in that it can allow us to do chemical composition, much like we might think of doing on, say, a gas chromatograph, but it'll also allow us to do physical properties, where we might have expected to have to use a dedicated physical properties analyzer. So we can do both compositional analysis as well as physical properties off of one measurement, off of shooting one beam of light across one sample. It comes down to using different algorithms. Also, because it's fast, we can switch streams quickly and do multi-stream analysis. So we can use one stream to do what multiple analyzers might typically have been doing. It's all solid state, no moving parts except for one that's built inside of kind of an IC, a tunable Fabry-Perot filter, if you like. But so what it means is that it has no moving parts. There's no parts of the actual spectrometer that are in contact with the fluid, except for a flow cell that we're going to talk about in a little bit. And as a result, we can have very little maintenance requirements, very high uptime, virtually no maintenance, no sample conditioning to speak of. Arguably putting in things like probes and transport lines, that's part of a sample conditioning system, but it's very minimal sample conditioning, doesn't require a dedicated analyzer shelter, doesn't have consumables like carrier gases, so it can reduce system complexity and cost. The technology was launched in North America originally, and we've seen it rapidly displacing gas chromatographs, mechanical physical properties analyzers like RVP and vapor pressure analyzers, as well as people putting it in place to replace manual sampling and grab sampling.
Measurement of
the JP3 Verax family of analyzers are optical spectrometers that use advanced data processing techniques, what we often refer to as chemometrics. Chemo coming from chemistry, obviously metric coming from measure, using mathematical algorithms to be able to look at an infrared spectra and pull chemical data, measurement data out of that spectrum and allow it to be used for process control. It allows us to do a wide range of measurements in near real time and at process operating conditions. So one of the important things to realize with this technology is we don't tend to have to put in things like regulators or control pressures or change temperatures. We typically run the sample directly at process operating conditions. And what that means is, assuming the sample was single phase when it was in the process, it's single phase now when it's in our analyzer. And this is really important because in a lot of our traditional analyzers, we'll mount an analyzer building far away from the process, bring a sample over there, and perhaps do things to control flow rates, temperatures, and pressures. It's one of the things we commonly do in sample conditioning. But all of those, every time we have a temperature or a pressure change, we have a possible phase change as well. And so by running at line conditions, we can try to make sure that we keep the sample in the phase that we want to do the measurement in. So we can use this to do hydrocarbon composition and everything from refined products like gasoline, natural gas liquids, condensates, natural gas itself. So we can do both gas phase and liquid phase samples with this. We can do measurements directly in crude oil. It's one of the things that people are often surprised about is that we can use an optical or a spectroscopic technique in crude oils. And people think, well, it's such a dark fluid, we're not getting any light through it. But in the near infrared region of the spectrum, we actually get good optical transmission and can see the absorption bands from the hydrocarbon. We can also use this to do many physical properties. A lot of our physical properties of hydrocarbon fluids are related to the types of bonds that are present and how many of those bonds are there. And so since the infrared region of the spectrum, the photons interact with the vibrations of the chemical bonds, there's a lot of physical properties that we can predict by measuring the near infrared spectrum. And these include things like density and API gravity, vapor pressure, boiling points, and boiling point distribution curves. So we can look at a crude oil, for example, and do almost a simulated distillation. We can get the boiling point fractions at different temperatures and predict those. For gasolines, we can do things like octane numbers, RON and MON. For diesels, we can do cetane number. For jet, we can do things like fleet freeze and flash points, BTU content. There's a lot of different, we can do viscosity. There's a lot of different physical properties which can be predicted once you've built a model around the near infrared spectra of that material. We have to remember that when we're looking at the spectroscopy of these things, we're looking at the bulk spectrum. We're looking at all of the components at the same time. As a result, we can tend to do a good job of measuring bulk components, typically things that are there in the mole percent ranges, greater than 0.1 mole percent. This isn't a technology that we would typically use for trying to look at trace components present in the mixtures. So, if you're looking at, say, doing ethylene production, you can look at the ethylene and other major components, but you're not going to be able to look at, say, parts per million of acetylene in your ethylene by using this sort of technology. So it's generally a bulk components, bulk physical properties type analysis. So the way it works is we'll have a process line, some chemical process, whether it's crude oil plant, whether it's product NGLs, from a deethanizer bottoms, whatever. We have sample continuously flowing through that process line, and we look for some source of differential pressure. It might be something like an orifice plate. So we have sample flowing through that process line, create some differential pressure across that, say, orifice plate, or it could be pump or a process filter. We use that differential pressure to drive process fluid through what we refer to as a flow cell. This is where the fluid flows through essentially a stainless steel block that has 2 sapphire windows in it that we're shooting the beam of light across. We mount the analyzer someplace else, someplace remotely, connect it to that flow cell via fiber optics, and shoot a beam of light over the fiber optics and let the beam of lights to come back to the analyzer. So, I usually refer to this as being the brains of the whole device. So the important things here to realize is that any process fluid that is leaving the process is being returned right back into the process. We can mount this close to the process because it's going to run at process line conditions anyways, so we may as well have it as close as possible. That lets that fluid flow over there quickly, and no fluid flows over to the analyzer. So wherever we put that analyzer, we don't have to worry about things like, do I have to put toxic gas detection in? Do I have a carrier gas and might I have oxygen deficiency? It allows us to put that analyzer at some place like a MCC building or a control room. The onboard computer then looks at the light that comes back, and from that makes an analysis. So what essentially we do then is take the spectrum that comes back. So this is the NIR spectrum. We take that near infrared spectrum, run it through the algorithms that we've built into the analyzer, run it through the models that we've built, and use it to predict, say, chemical composition. So for example, in this case, we've showed a wet natural gas type sample. But it could be crude oil, it could be condensates, NGLs, refined products like gasoline. And in fact, since one analyzer can handle multiple flow cells, we can put one of this unit in and have different flow cells measuring different things in different places. So one flow cell might be measuring a natural gas sample, another one a crude oil sample, and still another a natural gas liquid. So again, we can have up to 4 process streams on a single analyzer. This one has one spectrometer and switches which set of fiber optics the beam will go out. Each of those process streams we can be doing different analysis on. So we may be doing distillation curves and vapor pressures on one set of sound on one measurement point. We may be doing cloud point, say, or freezing point on a jet fuel that's being produced at a refinery, and still another point, we can be looking at the gas phase overheads of a distillation tower. All that data that's coming in, the results of the analysis, are being communicated out to the plant's distributed control system or SCADA system via Modbus over Ethernet or via Modbus over serial. Typical applications include gas processing and natural gas liquids plants. So we can look at, yeah, we have a question in the chat. Just, is the sample homogeneous during extraction of the sample cell? Generally, the sample probe must be 1/3 to 2/3 of the pipe ID for extracting homogeneous samples. Yeah, we look for getting, we still have the requirements of looking for where to get a good sample from. So, generally we want to be a few pipe diameters away from an obstruction, sampling in that central third region of the pipe. We'd like to, if we're ensure that the sample's well mixed. So in some cases, we may recommend that there's a static mixer upstream so we can get a well mixed sample. That's going to allow us to ensure that we get a sample that's representative of what's in the process. So again, we can use this in gas processing facilities for things like condensate stabilization, for looking right across an entire fractionation plant. Again, the beauty of this is we can do both gas phase samples and liquid phase samples. So we can look at the liquids in a tower bottoms and the gas phase in a tower overheads with a single analyzer. Also, unlike some conventional technologies, we don't have to say pick a different column for doing a different analysis. We can do the same hardware. We can really do a light hydrocarbon analysis of C1, C2, C3s, and be looking at crude oil. And so we don't have to pick different columns and things like that for the analysis. Density of LNG, question here from in the chat. Density of LNG condensate can be measured using this analyzer. Yeah, density is one of the things that correlates very well to the near infrared spectra. So if we're doing a condensate, we can use this for doing a density analysis. And so on, oftentimes we will, a bunch of questions coming in. A couple questions I'll answer right away. So oftentimes, we can be doing things like density along with the compositional analysis as well. And again, when we do it by inferential methods like NIR spectroscopy, we don't calculate the density based on what we predicted the chemical composition to be. We build a complete separate model for that. So one of the questions in the chats was comparing the JP3 with the ABB FTNIR. Great question, because FTNIR, when we talk about this technology, we often talk about it like it's a new technology. And what JP3 does is a new technology. But using near infrared spectroscopy to do these kinds of analysis has been around for a long time. And one of the common methods that has been done in refining and petrochemical applications has been done using what we refer to as an FTNIR, or a Fourier transform near infrared. Great technology. Has historically tended to be more maintenance intensive. FTNIRs typically use a set of moving mirrors that are going to be for want of a better term, without going into details about how an FTNR works, if you like, the wavelength selection to scan the whole spectrum is done by having these mirrors that move and have to be precisely aligned, and their movement has to be monitored to very high precision. And so historically, they've been used a lot in refineries and in places where there's analyzer technicians always available to perhaps do some maintenance on these devices. Historically, and some people may argue with me on this, one of the issues has also been you have to calibrate the wavelength axis of these devices. And so historically, transferring the models from one unit to another has been difficult, or potentially had some issues. A couple of the unique things about the JP3. The light source is a broadly tuned laser. So it's a superluminescence LED in a cavity, laser cavity, that has a little tunable Fabry-Perot filter in there that is changing the wavelength that the cavity can transmit. So it becomes a monochromatic laser beam that sweeps across the range of wavelengths. And so from a spectroscopy perspective, Beer-Lambert law says, we'll be able to get a real good linear absorbance measurement if we have a monochromatic light source. This is a monochromatic light source that steps, we typically step at every half of a nanometer across the wavelength range that we want to measure in. So we can get typically higher resolution spectra than we get on an FTNIR. We have the advantage of a laser light source in that it's extremely bright. It has a built-in wavelength calibrator, another temperature-controlled Fabry-Perot, that allows us to get an exact wavelength match from one spectrometer to the next, so we can transfer models very easily. It's been designed to have no maintenance. So historically, it's been easy to put an FTNIR at a refinery where there's a lot of technicians, but very difficult to put an FTNIR at a remote gas blending skid or a crude oil blending skid out in the middle of nowhere, because no one's there to do maintenance on it. Mercury analysis in wet and dry gas. Mercury is not one of the things that we can do with the near infrared technology, whether it's an FT or not. Mercury is not an NIR absorber. Mercury tends to get done more by kind of ICP, lost it. We generally will do it by doing an atomic absorption or an atomic emissions. Calibration frequency, great questions, boy. Calibration frequencies for the JP3 models. Again, a good question, because we have to build models for these types of devices. And so what we want to see is the range of different products that are going to be produced when we make the model. So when we do an installation, we like people to kind of swing their process around to let us get spectra from different operating conditions, assuming that product feeds haven't changed the facility much, and that we're running along the same, in the same general area. We can have models that are good for a year or years. If there's variation in the process, if you're bringing in, say, a whole new field, or you're bringing in a new importer of crude, it may be necessary to add more data into the model. So we typically recommend, especially since we're putting in these in applications where having the analyzer there adds value to the process, we typically recommend every 3 or 6 months to pull some additional samples, see if they're fitting in well with the model, and if not, add more data into the model. Now, These analyzers are doing a statistical analysis as well to say, how good does my current data look like what is already in my model? So I can use the results of that statistic. We basically provide a statistic to say, we think the analyzer is matching up really well with the range of things it's calibrated for, or we can also provide an output that says, based on the statistics, the product that you're putting through the analyzer doesn't look like it fits in really well with the model, and we would recommend that you add more data to the model. So the calibration frequency is variable really based on how much process change and feed changes you really have. Also, you may have things where you do winter gasoline and summer gasoline, at least in North America, because of the big changes in temperature. We allow different vapor pressures and butane contents. So then, if we're going to mix essentially a different product, we have to do model updates. So again, from an applications perspective, common applications is gas processing and NGLs, full fractionation trains. So that could be gas processing or the fractionation train, even within a refinery. We'll look at refined fuels for pipelines and terminals. So we'll look at identification of which pure product it is. We'll do quality determination to say, is it on spec? Does it meet its vapor pressure spec or its API gravity spec? This will allow us to do butane blending for things like vapor pressure and octane. We can also look at it because we can tell the difference between, say, jet fuel and diesel fuel and gasoline. We can look at it in pipeline applications and terminal applications for looking at batch interfaces. And then blending of also purity products as well. So we see it, in things like crude oil blending, in gasoline blending, etc. And certainly butane blending into those products. And again, crude oil can look at full distillation curves, give you an estimate of, this crude will kind of give you what the boiling point fractions are, so you know how much is going to get produced from different trays, if you like, of a crude distillation unit. So if a crude doesn't have anything in the intermediate hydrocarbons, if it's got a lot of light ends and a lot of really heavy ends, you can end up with you're not using all the trays to full effectiveness. So again, from the benefits of this technology is very fast, field deployment with minimal production. We don't have to build complex analyzer buildings, low operational costs, multiple measurements from single instruments, very low maintenance costs, and high reliability and uptime. On the gas processing side, we're going to focus a little bit on the gas processing side for a while. Where these have been commonly been used is to optimize natural gas and NGL processes from production, looking at what's coming in on plant inlets, all the way up to final products. So we want to look at natural gas production, my BTU spec, especially, or my pipeline specs for rich gases. We want to look at gas processing plants, at fractionation, and at blending. So common applications are going to be that we see in gas plants are going to be, I'm going to jump in on that question just in a minute. I'll finish the slide and I'll jump to that question. We've used these a lot in natural gas processing facilities. Everything from doing BTU analysis and C1 through C6 plus analysis on the gas phase side, to NGL liquids composition, vapor pressures, condensate vapor pressures. We can do very rich gases that can sometimes be difficult to do because of the fact that they're right at their dew point. We can get a hydrocarbon dew point and bias the results if we let them cool off. But again, because we measure right at line conditions, we're measuring the same phase that's there. We do gas plant condensates, what some people refer to as natural gasoline, C5 plus streams, Y grades and NGLs. So it's things like deethanizer bottoms, depropanizer bottoms, debut bottoms. Fast measurement works great in cryogenic separator type applications. And again, we can look at overheads and bottoms of the single analyzer. So in comparison against, when we talk about it comparing against GCs, yeah, we see a number of advantages in the speed and simplicity of operation. Other technologies get used typically for some of the applications that we might not consider doing with a JP3. So UV vis is very good for doing trace levels of, say, H2S in natural gas. Again, not an application we would do in the NIR. Mass spectrometers, they're very good with gas phase samples. And a question about trace level stuff. Generally, we don't do trace level measurements, or I shouldn't say generally, we don't do trace level measurements. Typical detection limits are down around 1,000 ppm. It's kind of the measurement range we like to work in. We do less than that. We do, sub 1,000 ppm, say propane in condensate, or low levels of, say, butanes and pentanes in natural gas. But generally, we're in that 100 to 1,000 sort of part per million range, not things that are down in the single digit parts per million.
Hi, Phil, can you hear me?
Yes, sir.
Sorry to interrupt you. Just wanted to confirm that if you cannot go less than 1,000 ppm, so that means that the C1 or C6 plus analysis of natural gas, you cannot measure the pipeline quality natural gas, which has almost 93% of methane in it, because all the other components will be less than 100 ppm.
No, that's probably not completely true. Generally you'll see, like you say, a typical pipeline quality natural gas will be like 93% methane, say 2% CO2, in that percent levels, partial percent levels for the ethane and the propane. And that's why, it's hard to generalize these things. When you get out to the higher molecular weight hydrocarbons, they tend to separate themselves a little bit from where the light ones are. And so in the gas phase, we can get that C5 and C6 concentrations typically to be measured. And again, the US side has done probably more of the gas phase applications. So I don't know if Nate or G, you want to comment on that? I got another question here about H2S, hydrogen, CO2, N2. In H2S, no, not in the ppm levels. Hydrogen and nitrogen are not near infrared absorbers. CO2 is. So CO2 is measurable. Generally H2S, hydrogen, N2 not. N2 and basically inerts are done by normalizing the stream composition to 100%.
Okay, for BTU measurement, do you use GPS standard, NX19 or GPA?
No, we model the BTU as a separate. There is a standard being written right now through GPA for using NIR for doing analysis of natural gas and natural gas liquids. But we build a model to actually predict BTU content. So we do run separate models for each chemical and then a model to do the BTU content. But what we do is we correlate it. See, because we build models and base the modeling on lab analysis and the lab analysis may be being done to an appropriate GPA or ASTM standard, we're building the model so it correlates to the lab standard. Basically, what we're trying to do is build a model that says, were you to pull a custody transfer sample right now, we're going to predict what you would get if you sent that off to the lab. That's essentially what the model is doing. And so where it generally fits in is to allow for tighter process control so that if the analyzer models are running and saying you're going to be on spec for BPU or API gravity or whatever, you can use that to control your process. And as soon as there's an upset that where potentially you could be making an off-spec product, the analyzer will see it, give you information, and allow you to pull back to being on spec. So generally, we see it more as a process control, process monitoring device than a direct custody transfer device. Does that make sense?
Yes, thank you. Thank you for the explanation. Yeah.
So the sort of applications we can look at is any kind of a fractionation vessel. If we've got a distillation tower or a condensate stabilizer tower, we can be putting sample points from the JP3 on the inlet or on multiple inlets to that tower, on the bottoms product, and on the tower overheads. And so we can again have one analyzer that's looking at all of the streams that are feeding this unit, and also all of the product streams, and attempting to provide information for both feed forward control, changes on the inlet side, and then looking at product quality, changes on the outlet side, and allowing us to adjust the operating conditions, process control back, feedback back to that cryo unit, whether we're going to adjust temperatures, pressures, relative flow rates from different feed streams. Once we have all that data about this is what the product coming in looks like, this is what the product going out looks like, now we can start to do optimization. And that's where the inherent value comes. Because if we can optimize it and say, if the liquids product is the most valuable one to us today, we can adjust the operating conditions of that cryo unit to try to maximize liquids production. Or similarly, we can say we want more slipping to the gas phase if our goal is to produce increased natural gas volumes. Again, we can put this right.
Just to confirm one thing, just to confirm in your
Yep.
backside, what you're saying is that the one model or one analyzer with 4 separate flow cells installed in 4 separate lines of this coordination unit, it can simultaneously measure the compositions and the physical properties like reed vapor pressure and other things, right?
Yes.
Am
Yep.
I good?
Yep.
It will measure the composition, the dry BTU, and the physical properties as well.
Yep. So I'm going to be looking at, say, the gas phase that's coming into this cryogenic unit and doing an analysis of that. I can have a vapor pressure analysis on some condi, for example, on one stream. I can be looking at my sales quality natural gas. And as you see here, again, now we're down in that 0.03% for the propane in this stream. So on gas phase, we can tend to go a little bit lower in concentrations. Liquids is going to be more difficult. And then we can look at the full liquids analysis on that NGL bottoms.
And we don't need any modification for liquid analysis or gas analysis. Same simple flows will be used for both.
The only difference between typically what we use in a liquids analysis and in a gas analysis is gases have lower molecule densities. So we use a little bit longer flow. So we put a larger gap between the windows in the flow cell to give us a little bit longer optical path. But the JP3, the brains part, is identical to all of them. It sends the same beam of light out over the same fibers. And the only thing is, for gas phase applications, we often use a 1 centimeter flow cell. And for liquids, we use a 0.2 centimeter flow cell.
And we don't have any restriction about the inlet temperature and the pressures.
Only from a certifications perspective. You know, the flow cell is rated to 1500 PSI. And the standard flow cell for in Canada now, we have some special boiler safety requirements. So a standard configuration for us is to 1500 PSI and 107 degrees C. In the IEC version, because you don't have what we have a special Canadian boilers code, pressure code. In the IEC versions, you can go to higher temperatures than that. It comes down a little bit though to how high a temperature the fiber optics are rated for. The high temperature cells, I don't remember, off the top of my head, 160 C?
Yes, the 500 degree F
Okay.
is, yeah.
So yeah, high temperatures, high pressures. So again, you know, this allows us to put one analyzer looking at multiple different liquids and or gas phase streams within a plant. And so we can look at everything from inlet gases to tower bottoms to tower overheads, final product. You know, as we're going to talk about, we can even look at the fuel gases, say going to a burner. So fuel and flare gases. This allows us to do things like NGL blending. So we can often slip, say, some ethane in with our propane. I think it's 107 degrees C stream temp for flow cell, isn't it, Mohit? And typically there's two versions of the analyzer. A single flow path, so one stream. There's a version of the analyzer that only does one stream, so it's really useful for something like a crude oil blending skid. Or there's a 4-stream version that allows us to measure at 4 different sample points.
Yes, I think the high temperature one is more than 100 degrees C. You're right.
Yeah. I think the high temperature one is closer to 230 C, and the standard I thought was 107, but at least that's how we saw them in Canada. 232F and 500F, I thought were the common 2 temperature ranges. So we can get an uplift, we can get an increase in our propane volumes if we can blend some ethane in there, as long as we're meeting specifications. So what we want to do is run as close to the maximum amount of ethane in there. Since ethane doesn't sulfur as much as propane typically, we are going to try to blend as much ethane into that propane as we can and still meet specifications. And so this gives you an idea of some typical ethane levels and propane levels that we see. This is a deethanizer bottom for an application we have here in Canada. So what I typically plot is on the x-axis as I plot the lab values. On the y-axis is the NIR. And so what we see here is an excellent one-to-one correlation between what the NIR analyzer gives us and what the lab gives us over a wide range of concentrations. So this is going from as low as 2 LV per liquid volume percent to as high as a 9 liquid volume percent in the for the ethane analysis. And then at the same time in that stream, we're measuring the propane. The control variable here is typically ratio of the ethane to the propane. And so we're going as low as 55% to as high as about 74% on the propane. And again, when we compare the NIR results to the lab, you get to see that on the ethane, we agree with the lab to within about plus or minus 0.2 liquid volume percent. And again, this is over a fairly wide range of, they're running this deethanizer over a fairly wide range of operating conditions. This is, 5 months worth of data between 62 degrees F, so call it 17 C to about 28 degrees C, and 110 to 170 PSI. So what's that? 7 bar to about 12 bar, 11 bar. Similarly on the propane, we're measuring typically at 55, let's call it 65 LV percent, and the NIR agrees with the lab values to within plus or minus a half an LV percent. So, on the propane, we're seeing about 1% a read. Question in the chat about how far can we take the stream from? Should the tapping point be close? Ideally, we like the tapping point to be close. Whenever we're putting in a process analyzer, we usually like to keep our sample lines as short as possible, because they're going to contribute to part of the time delay. And the longer we run the lines, the more pressure drop we're going to get along the line. So when we do an installation, if we can, we'd rather run very short fluid transport lines and run longer fibers if we need to. Because remember, we can mount the analyzer anywhere. So we can put the analyzer in an existing building and then run our fibers out to that sample point and back. We don't bring any fluid to the analyzer that way. We're just doing the letting the light beam interact with the fluid very close to the sample point. And so by keeping it short, those lines, we will be less likely to get pressure drop and phase change. That being said, it's not a requirement. If you have, for some reason, let's say you already have an existing analyzer building and you've got a fast loop running to it and it's 100 meters of sample transport lines, as long as you think you have a good representative sample in that building, well, we can put the flow cell right there too. So we've done it both ways, but our preferred installation is to put the flow cell as close to the measurement point as possible. And that's preferred simply because we're less likely to see phase change and we're going to get a faster response.
Hi, Harris. Are you hearing me?
Yes, I am.
Is it clear?
Yes.
Okay. Okay. Guess I have one question. Actually, I'm working polyethylene plant, and actually the reactor is far away from purification site. So we have, the main analyzer close to the reactor site. Okay, but there is sometimes switch to the feed stream from battery limit, and that stream is far away. It's around 300 meter from the analyzer. So I don't know, your analyzer could able to measure this, within 300 meter or more. I don't know how far, because you mentioned in your description just now, you mentioned that we have many streams, like 4 or 5 streams coming from different location of the plant. So if it is, as you said, that because of pressure drop, maybe it will not be very precise. So how precise will be? If we have 300 meter or more, I don't know. Can you specify the distance?
Sure. I think the longest fiber installation we've done in Canada was 1,100 feet. So that's about 340 meters or so. We can run the fibers for a very long distance, but the type of fiber we use is relatively expensive. And so ideally, we like to try to keep the fiber length short. But, you know, if you were in a situation where you had, let's say, I've got vessel number 1 and vessel number 2, or plant inlet, you know, maybe this is my inlet. This is where my inlet is, right? And this is the vessel I normally want to measure. If we could put as long as we could mount the analyzer part in between, you know, then we end up with about 150 meters of fiber going in each direction. And that would be fine.
Okay, so material is fiber for the piping, huh?
Yes, yeah. So what we would do is, I'm sorry, I apologize in advance. I'm not a very good at drawing, but
It's okay.
what we would do is we would put one of those flow cells, one of the measurement cells at each of these places on tubing. So this would be something like, you know, we typically run 1/2-inch pipe. And let's say we have 5 meters of it. So this is just going to allow a continuous sample of fluid to be flowing through each of these flow cells. And then to each one, we would have a fiber that goes out and shoots a beam of light into the flow cell, and then, and then a fiber that comes back and brings that light back. Same with the other one, a fiber that goes out and a fiber that comes back. So we would have piping to get liquid over to the flow cell, mount the flow cell close to the process. So again, we don't have much pressure drop along the lines. They're nice big diameter, so they don't plug easy. They don't get, you know, in polymer plants, we sometimes worry about plastics forming in our transport tubing and starting to plug off our lines. Well, if we can keep them large diameter and relatively high flow rates, that helps us, and we don't let them change temperature from the process, then we don't get as much plugging. So we run this continuous flow through the sample cell, send a beam of light out on one fiber optic, pick the light up that went through the sample and bring it back over to the analyzer.
Okay, is it clear? But actually what we have piping, stainless steel piping for 300 meters. It's not a fiber.
Okay.
Fiber
Okay. Yep.
Yeah, this is what we have.
So you already have okay. So then your concern, I mean, my concern when I hear of 300 meters of sample piping is always, does it stay single phase all the way along there? That's a really long sample transport line.
Yeah, it's very long. Yeah.
Yeah. And so, you know, you have to be concerned about how long at the flow rates you're at, how long does it take to get through that line? And do you still have a representative sample by the time you get to where you want to do the measurement?
Actually, we have doubt in that results. Because of this, I am asking this. Yeah.
I would doubt it too. Sorry to say. Especially because distillation towers are hard, right? Anytime we're using doing a gas liquid separation in a tower, the liquid at the bottom is generally very close to or right at its bubble point, and the gas at the top is right at its dew point. So temperature and pressure changes along the way can cause us to get phase changes.
Okay. Thank you, Aris. Thank you. Thank you for clarification.
Thanks for the question. And I apologize, people. It looks like I'm going to run a little bit long, but I understand completely if you have to go. But you know, I'm happy to continue along here a bit. So again, you know, we can use the analyzer to look at, let's say, the bottoms of a condensate stabilizer. So in this graph, I'm going to focus on this graph over here. In this graphic, we're using the near infrared analyzer to analyze the C3 and the C4 hydrocarbons in the stabilizer bottoms. And so the x-axis is the lab results. I show different ranges for the lab results shown on the bottom as the top. The C3 and the IC4 were varying between 0 and 1.4 liquid volume percent. The NC4 was varying from about 1.5 to 5 liquid volume percent. So the blue dots are the propane. You see those all clustered down between the 0.2 to 0.4 LV percent. So you can see that, you know, we tend to be kind of conservative when we say, well, we can only go down to around 0.1%. A lot of this data is still quite good on that propane side, and it's down below 0.2, 0.1 liquid volume percent. It's just our precision isn't as good as we get to really low concentrations. The red dots are the isobutane, and it varies from as low as 0.2 LV percent to as high as about 1.2 LV percent. And you can see the near infrared analyzer results on the y-axis on the left-hand side. Again, we get great correlation between the NIR results and the lab methods. Then the green dots are against the right-hand y-axis and the x-axis up at the top of this graph that goes from 1.5 to 5. And the green dots are the N-butane. So we're measuring 3 different components here with NIR on quite different measurement ranges and showing here that we have a great degree of accuracy or agreement between the lab results and the online analyzer. And this is, again, this is a complex stream. This is a stream that has everything from C3 to probably C15 hydrocarbons in it. So we have a lot of potential interferences, but we can do a great job of measuring, say, the light ends in this stream. We can take the same analyzer, run a separate flow cell over to a gas phase stream and use it, let's say, to analyze a rich natural gas. In this case, it's about a 1200 BTU gas for feeding into a gas-fired compressor. And so this allows us, again, because we have this fast response, we can do, you know, near real-time analysis and do full front-end burner control based on understanding what the BTU is. You'll see that we do both. We're showing both the BTU and the relative density here. So that means we could also calculate from those 2 numbers the Wobbe index, where we can calculate carry, the combustion air requirement index. And so from those 2, you know, those sorts of things, we can calculate how much air do I need to get the most efficient, lowest emission burn from this fuel. So we can use the analyzer to do a complete fuel gas analysis and optimize burners in compressors and power plants. I can try to go a little bit faster through a few of these extra slides. I really do appreciate all the questions, and please feel free to keep asking them. It's just had me running a little bit slower than expected, but I think it's great. These sorts of questions clarify things for everybody else who's here. So we can do real-time optical measurements of refined fuels as well, gasolines, naphthas, jet fuels, etc. Things like flash points, freeze points, viscosities, vapor pressures. So, you know, there's many physical properties of these refined fuels that we can do with NIR spectroscopy. And this allows us to do applications like blending, where we want to add butane into, let's say, our gasoline. So, butane is generally a lower value product than gasoline. If we can add butane in and still, for example, meet our vapor pressure specification, it allows us to sell, to basically increase our production volume of the gasoline by blending the butane in. I will note as well that, this graphic that's shown here. Oh, great question, Paul. I had a slide right at the end that shows the certifications. Yes. ATEX, IEC, and CE mark for sure. Class 1, Zone 2. The flow cell part is Class 1, Zone 1. But I'll show, got a slide right at the end that shows the actual cert. This graphic here is an actual screenshot from software that JP3 provides to customers to be able to look at how their analyzers are running. So all of the analyzers actually have a cellular modem in them. And via that cellular modem, you can pull up the data from anywhere in the world. You could be sitting on a plane and basically say, how's my butane blending running right now? And you could pull this exact graphic up and look at how you've been running, what you're currently reading for, let's say, vapor pressure, and any other, there's a bunch of other parameters we can pull up into that results table. On refined fuels, we can do distillation curves. Again, and there are a couple of questions about alternative analyzers. I'm going to deal with those right away. So, in refined fuels, we can do vapor pressure, octane numbers, initial boiling points, final boiling points. And again, we just let you know which ASTM standards we're going against there. Typically with refined fuels for vapor pressure, it's D5191. We can do parameters like density, distillation curves, again, flash points and freezing points for things like diesel and jet. The question in the chat is comparing, say, the JP3 technology with the guided wave, which is another NIR, or the Bartek Benki, which is a traditional vapor pressure analyzer. I assume when you're thinking about the Bartek Benki, you're thinking about their vapor pressure analyzer. So on the guided wave side, guided wave uses what we refer to as a dispersive spectrometer. It's a diode array-based device, a silicon chip that has a whole bunch of photodiodes spread along its length. And then it uses a grating, like the way a prism does, to spread the incoming beam of light out into its individual wavelengths. Again, great devices, lots of applications. The JP3 spectrometer has, in my opinion, a couple of pretty significant advantages over what guided wave does. Guided wave requires that you use a broadband light source. So it's some kind of a thermal source, and then disperse the light to hit the photodetectors. And the issue is that, potential issue is that every spectrometer has a different wavelength calibration and a different sensitivity. And for dark fluids, it can be difficult to get enough light to go through them. On the JP3 side, the fact that it's a monochromatic laser beam that is being shot through the sample makes it easier to get a lot of light through. We can operate at higher resolution than the dispersive devices do. The guided wave is only typically going to give you on the order of a couple of nanometers of resolution, whereas we can go down to about 0.1. And so we can get more data points in the spectral region of interest, which gives you better statistics in your modeling. You also have the advantage that the x-axis of the JP3 spectrometers are all calibrated exactly the same. So you can transfer models easily from one unit to the next. And we've demonstrated this again and again in the field. And on dispersive devices, model transferring can be difficult because the x-axes aren't exactly the same. In regards to the Bartek Benki, the Bartek, if we're thinking about vapor pressure, it's a traditional true vapor pressure analyzer in that it's a movable piston. The problem is it's got, again, very tiny tubing and moving parts that on clean samples can work really well. On samples, when we're trying to do things like vapor pressure of crude or condensate stabilizer bottoms, samples that are going to be more likely to have things like sand, clay, asphaltenes in them. Anything that's got moving parts and relies on tiny, tight precision O-ring seals with moving pistons generally needs a lot of maintenance. So in fact, my understanding is that Bartek has said they won't sell their vapor pressure analyzer now for crude oil applications, only in refined fuel applications is what I've heard. I'm not sure if anyone wants to corroborate that or, not good question. Ambient temperature range is from minus 20 degrees C to plus 55 degrees C.
Flow cell is 70 plus 70 degrees C, and 55 will be on the analyzer side.
Yes, exactly. Yeah. The flow cell can be hot or cold, minus 40, but the analyzer itself, electronics part, is the hazardous area certifications from minus 20 to plus 55. Generally, we like to see it in a building that has some temperature control. No, depending on the ambient conditions, you may just want to put a sunshade over it. So the question was, it won't require cooling. No, you don't have to put a Vortex cooler on it or something like that. So another interesting application for the JP3 is looking at pipelines where we have different fuels going down them. You're very welcome. Thanks for the question. If we have different fuels going down or fluids going down a pipeline, we can look at the interface in there, what we refer to as the transmix, the mixture that occurs during transportation. We can look at the interface and determine when we went off spec for, let's say we were flowing diesel. We can determine when we went off spec for diesel, but we're not yet on spec for the next fluid, say jet fuel. And then we can say, okay, this is good jet fuel now. And then if we have another transition, let's say between jet fuel and gasoline, we can identify that transmission as well. And so what people usually do is during the transitional parts is put that fluid to storage for reprocessing. So what we're able to do is minimize the amount of fluids we have to reprocess and maximize the volumes that we can push down the pipeline and push out on-spec product. And in fact, JP3 recently has been awarded a patent on advanced interface detection software. I'm afraid I'm not great at octane boosters and blending, so I don't know. I would imagine if they built the model around it, maybe one of the JP3 guys can comment. I'm again more on the Canadian side. We tend to produce a lot of hydrocarbons, but have less on the refining side. The US side has, of course, got some, a large percentage of the or much larger refining side. Because I'm afraid I don't know about blending in an octane booster like N-methylanilene.
So what we're trying to say here, Phil, is that, you know, if we don't want to have the whole modeling done for octane numbers, flashpoints and all, we can still using the, you know, the AI modeling, we can still detect whether it's a, you know, clean product like a premium, it's a diesel, or it's a interface or no interface condition.
Yes.
So that's what this new model does.
Yeah. Yeah, no, there was a question in there about octane blending though. Yeah, so the ADA, the advanced interface detection, lets us see interfaces without having to build, let's say, a model for each of the products. So what it allows us to do is let the device almost self-learn, if you like. I'm saying, I can tell, if you tell me you're on spec, we ran a product that looks like this for a long period of time, and then we ran a different product. From a chemometrics perspective, if you like, when we do the full compositional analysis, we're doing more of a regression type analysis, something like partial least squares and latent variables. What ADA is kind of doing is more like a cluster analysis where it says, this product belongs in this cluster, this product belongs in this cluster, and there's stuff that shows up when they're mixed together that doesn't belong in either cluster. So we're at an interface. So it allows us to do that clustering and interface analysis, if you like. And so we can tell when we're on spec for, you know, this group of products, say the premium sits in one cluster, this group of products sits in another cluster, this in a third cluster, and we can tell which product is or when the transition is in the region where we're not on spec for one product or the other, when a transition is happening. So we can use ADA again to do transmix, but it becomes less modeling intensive than if we're trying to do the transmix based on, let's say, I'm going to look at the octane numbers or whatever. On the crude side, we can do crude compositional analysis and vapor pressure and physical properties as well as looking at batch interfaces between, say, a light sweet and a heavy sour. And so it allows us to optimize, say, stabilization processes. If we're having to boil out some of the light ends in a heater treater, rather than running it on manual controls and having the temperature go up and down and the vapor pressure is constantly changing, we can measure the vapor pressure, put the analyzer as part of a control loop, and optimize the temperatures, and run a more stable product. This is some example data from a facility where they're blending light sweet, heavy sour, and butane. And they have an online traditional vapor pressure analyzer. The one I've shown is blue dots here. This is the traditional analyzer. You know, a moving piston type analyzer. X-axis here is lab results being done to ASTM D6377, I believe. And what we've got there is 200 data pairs where we've had a traditional online analyzer doing the measurement, lab doing the measurement, and the JP3 near infrared doing the measurement. And you can see I've made the data points fairly big to indicate that there's some error in both the X and the Y axis for these data points. The lab method itself has actually only got a repeatability of 2.3 kPa. So what we see is we have excellent correlation between the lab and the JP3 results, the JP3 and the traditional online analyzer results. The big difference, though, is during this test, which ran over several months, the traditional online analyzer was getting continuous maintenance, weekly calibrations, weekly maintenance, and the JP3 we didn't touch. So the advantage of this is that we can put an analyzer in and not have to do a lot of maintenance along the course of time that it runs. We can handle very heavy oils. This is, Canadian diluted bitumen. So basically imagine taking tar and diluting with butane and condensate. And again, we can do vapor pressures in this. The blue dots are the vapor pressures that were used in the model. The red X's are validation data that's showing that the model works. So again, we can get very good repeatability, very good correlation to the lab methods. Sorry, this should say D6377, as it is up here. I have to, deal with our American friends, so I put it in PSI at the top and KPA down at the bottom. This question about certifications. The new Verax ISX and IMX are out. They have full European certifications. So, there is our certification information. So this is for the electronics part. Zone 2C. And so, the typical operating voltages, 120 to 240 volts, 24 volt DC capabilities. The cabinet itself is IP66, NEMA 4X, communications RTU over TCP or serial. Again, you can use this in a wide variety of applications. I just gave you kind of some application information at the bottom. About to wrap up here again. Sorry for running so long. Some typical installations. You'll just see these get put outside. But certainly in the US. In Canada, because we get to -40, we put them inside of again, any available building that we have. And that wraps me up. If you have any questions, Mohit, who is here and has been answering some of the questions, is available and in the Middle East. You can get more information certainly from jp3.com. I've done a number of webinars about this technology for some of my colleagues in Canada and the US, and we have a full YouTube. Paul, good question. I'll answer right away. We have a full YouTube channel, has a bunch of the webinars we've done. So feel free to check out Inside Analytical Solutions on YouTube. If anybody wants to contact me, my email is there. Can we do water in crude? Generally, no. Typically too low a concentrations. Oftentimes water cut we're looking at, if it's at least for here, we're looking typically less than 0.5%. And water has this big, broad, mushy NIR absorption that doesn't give us good quantitative results. We certainly have been in situations where we've contacted clients and said, we're looking at your spectrum, it looks like it's wet.
Okay. So when it comes to inventory management of a tank farm, okay, and any given tank farm.
No, sorry, you didn't say tank farm. I just said inventory management.
Yes. Yes. 2 or 3 people talking at once here.
This is for which industry, Mr. Michael?
No, in the notes that PY sent me, PY, what you sent to Natasha, which forwarded to me. Okay.
Mute that guy.
I am muted. Go ahead.
There we go. Okay.
Sorry about that.
Yeah, no worries. So yeah, generally, no, we don't do water cut. So yes, JP3, JP3 was, so the question is, what's the relationship between JP3 and Flowtech? JP3 is the original manufacturer, yes. So JP3 was founded and runs out of Austin, Texas, and ran as an independent company for a number of years. About 2 years ago, was acquired by Flowtech, so Flowtech was a much larger company, traded on the stock exchange, and looked at the JP3 technology and felt it was a good addition to their company and the portfolio of products they'd like to be able to produce and the customers they would like to work with. and made an acquisition of the privately held JP3 to bring it into this publicly traded company. So JP3 remains as the original manufacturer, manufacturing on the same facility as it was before the acquisition, but has a larger company around it, if you like now. And so one of the things really is that, you know, at the time, JP3 was only selling to the US and Canada, North American certifications. And, you know, one of the things that's come up since the Flowtech acquisition has been bringing out the newer model with European, with international certifications.
So do you have any references in Middle East, installation references in Middle East?
Yes, and I'll be happy to support and guide you on that. So I can get in contact with you and talk about that.
Thank you. Thanks a lot.
Great. Well, again, my apologies for running over, but I thank you all for the interaction and the great questions. There's nothing more fun when you're actually doing a webinar or a presentation to have people interested enough to ask questions. So I really appreciate it. If there aren't any other questions, we'll wrap up here. If there's any, I'd be happy to try to address them.
Thank you, Phil. Highly appreciate this at 5 a.m. your time. Very commendable job. Thanks a lot.
Thanks. I'm going to go home and have a nap now. Thank you all for coming. Have a wonderful evening for those of you in Europe and the Middle East. And thanks to a couple of my colleagues from JP3, Nate and G, for getting up early, coming on this. Thanks for setting it up, Mohit.
Thank you, Claire.
Thank you, Haris. Thank you.
My pleasure. Thank you.
Thank
Thanks
you
for all the comments as well.
Thank you. Bye.
Thank you.
Have a great
For
day.
the audience for great questions as well. Thanks.